So the subject of this playlist is going to be the orthogonal diagonalization of a symmetric matrix. However, before we get to that, I'd like to review a couple definitions that will be used throughout the course of this section. So, with that in mind, here is a review of definitions for the process of diagonalization. So given an n by n matrix, that is a square matrix that we're going to refer to as A, an eigenvalue of A is a value of lambda that satisfies the determinant of A minus lambda I is equal to 0. Or consequently, this could also be lambda I minus A. Either one of those is fine, because ultimately it's going to wind up being equal to 0 anyway. An eigenvector of A is going to be a solution V to the system of equations created by saying that A minus lambda I, or lambda I minus A, once again, times vector V is equal to the 0 vector. Now, for each different eigenvalue of A, there will be a corresponding eigenvector of A. So ideally, we should wind up with n different values of lambda and n different corresponding eigenvectors of A. Now, the way that this eigenvector came about is that it also satisfies the following equation, that matrix A times vector V is the same as scalar lambda times vector V. So this comes from this. Now, in that ideal situation that I mentioned just a moment ago, if we do wind up with n different eigenvalues, counting multiplicities, and n corresponding eigenvectors, we say that A is non-defective. So A has a total of n, same as its size, linearly independent eigenvectors. In the case that it does have n linearly independent eigenvectors, it is non-defective. So the opposite of that would be defective. A has fewer than n linearly independent eigenvectors. Now, ideally, for situations of diagonalization, we need to have that A is non-defective. And the reason that we need that is for the generation of n by n matrix P. So P is going to be the n by n matrix whose columns are the eigenvectors of A. Now, in the situation that you can create P, that is where A is non-defective, if you can create P, then the diagonalization of the matrix A is multiply P inverse times A times P, in that order, to arrive at D, where D is the n by n matrix, the n by n diagonal matrix of eigenvalues of A. In the event that you can find P and multiply P inverse times A times P to wind up with a diagonal matrix where that matrix is all of the eigenvalues of A, then you have created the diagonalization of A.